My name is Michael Caisse. I work at Intel, and I like this picture because I started at Intel about 3 years ago, just under 3 years ago. This is a Lunar Lake wafer. It's the first device that I got to work on. And so in semiconductor world, you work on something and then like 5 years later, it shows up so the public sees it. And I'm very excited about this because it also is running software that I wrote. So let's talk a little bit about some of the constraints and problems inside of embedded world. I work in a group that deals with power management. So getting the device up, or the first thing to boot up, nothing else is up or running. There are hundreds and hundreds and hundreds of things on the chip, many of which you know about, many more that you don't. And they all have to be sequenced and brought up at a certain particular time. And then during runtime, it'd be nice if your YouTube video continued to run for a long period of time. You got to finish your movies. And so we handle power management during that time too. So our programs don't end. If our program ends, your CPU is shutting down. So you don't want it to end. So we live in an environment, and once things start up, they just continue to work. We don't use exceptions. We live in a world where we don't have dynamic allocators, and we don't have an RTOS. We've made the decision that bare metal is what we want. There are a lot of reasons that people might pick an RTOS. Usually it has to do with they want tasks and some type of primitives that allow coordination between tasks occurring. These things can just happen without that. In the past, and as well as this time, the talk really is going to deal with this development board. It's easily accessible by the public. All the code will run on this. It is an ARM-based core, and it has a whole bunch of different GPIO, communication all over the place, lots and lots of complex timers, analog digital converters, digital analog converters. These devices are, pennies, and you can just get tons of them, and they're fun to play with, and you can do a lot of stuff with them. The thing is, they are very complex. So when I say a timer, the timers are incredibly complex timers. Take a look at a previous talk of mine and kind of get an idea of that. But when we start thinking about how these devices work, all of these things internally, all of these different mechanisms that are trying to perform some task need to be serviced in some way. They either have data for you, they want to get serviced in some manner. And the way we deal with that is with interrupts. Interrupts, for our conversation right now, we're just going to think about them at the moment as if it's a hardware line coming into the device. And that hardware line will become active. When it becomes active, we might be in the middle of an instruction. So once the instruction completes, then we will go ahead and enter into our interrupt service routine. How that occurs is for this particular CPU, it understands that it needs to save some stuff off. So it takes care of that. That's the gray. It's going to take care of saving some registers off. And then it figures out that it needs to jump to a location, and that's based upon some vector table that's loaded in memory. And it says, oh, this is the address where I'm going to go, and I'm going to just start running. So it's going to just start running some code at that location. And when it's done, you say that you're done, and you go ahead, and the CPU itself, or the micro in this case, will restore the registers that it saved off, and then you can continue on. So interrupts are this really great way to basically change tasks. And so you can write task managers on top of them. You can use them in order to figure out what's going on with hardware. There are lots of great purposes with interrupts. Interrupts have different priorities. Lower priority numbers are higher priorities. So number 0 is the highest priority. As the numbers increase, they are lower priorities. And so if we have an interrupt that occurs, we're in the middle of our main, and this interrupt at priority 4 occurs, there's some amount of time that it takes for it to transition into your code. That's the saving the registers. And as we're in the middle of processing this, if we ended up with another interrupt coming in, lost my clicker. I went to sleep. That's even worse. All right, priority 0 came in, and priority 0 is a higher priority, and so we change context. Again, we save off the register set that we were in the middle of, that gray part. We continue now executing the code, then we restore, and then we jump back down into priority 4. So priority 4 we're continuing on the green. But meanwhile, while we're in the middle of processing that green priority 4 interrupt, another priority 4 interrupt came in. And now it's just saved in the, we're going to do that a little bit later as soon as we can get to it, because we're in the middle of a 4 already, so you can't preempt that. And you'll see that there is a very small line in between, but there's no gray bit that we have to restore registers because there's nothing to restore at that point. We can continue on and then we fall back into main. So this is the basic idea of how interrupts work. We're going to utilize those quite a bit. Now, we have an exercise. Before I share the exercise, Ben didn't know this was happening, but he's smiling because he's very clever. So I work with Ben Dean. Ben Dean is a very, very smart man. So smart, I haven't actually quite determined where the boundary is yet. And I thought you might be able to help me today. All right, so we need 4 volunteers, 2 of which I'm just going to pick because I want to pick. So Neil, congratulations, you get to be volunteer producer number 1. All right, Harold, you can be volunteer number 2, producer number 2. All right, I need a client 1 and a client 2. Any volunteers for being clients? Oh, here we go. Ian's going to be client 1, and in the back, client 2. All right, now some ground rules here, just so that you know up front what you're going to need to know. Your protocol is one in which you give all of the characters in reverse order. Okay? Unfortunately, Ian likes to have things spelt out in proper order, okay? Not reverse order. Do you understand? Okay. But playing the role of the proxy today and the coordinator of all this will be Ben. Thank you, Ben. It ends up that if you calculate a number, you can't just send the number over, you have to send digits, 1 at a time. It ends up, though, your client in the back would like to receive the data just as a number. All right? Okay, how this is going to play out is I'm going to move to the next slide, in which we're going to find out that the producers of the data have already received their messages simultaneously from Ben because he is proxying the clients. And now they're going to try to figure out what they have to do with their messages and then just shout out, all right? And then in your very best Tron voice, when you get to the end, you just say, end of line, okay? You got that? You gotta shout it out though. I'm losing my voice, so I'm not gonna shout. All right, everybody understand the rules? 1, 2, 3, go. As quick as you can, just yell it out. Just yell to Ben.
End of line.
You whispered it? What are you whispering for? Oh, you gotta start all over.
EULB. 1. End of line.
0. End of line.
Ben's very confused.
There's no instructions for me.
Ben, you need to, you had your instructions. I think we found the limit of Ben. Perfect. Oh. All right, okay. All right, so we understand, and I actually thought he got it. I was going to add a third person, a third route. That would have been maybe better. Yeah, and then we'll eventually, maybe each time I'm going to play this game, we'll figure it out.
Tell us how many cores Ben has.
So this Ben basically has 1 core, right? He's only able to talk, at least. He's got to serialize the data. He has some problems with, Harold is bringing in data, sending data. Neil's sending data. And Ben is trying to take these inputs and he has to bring them together in different spots, right? He can't mix them up. And this is what concurrency is about with asynchronous systems. We have different events happening in our system, and we have to marry those up with the data segment that they belong to. Does that make sense? Right? Like that is the problem of concurrency. All these things are happening, but they need to get to the right piece of data storage. And so there are 2 different ways to approach this. Well, there are a lot of different ways. But either you can basically say the event things, the things that are dealing with events, figure out where in the world the data is. So they're trying to find the data. Or the other way around is you bring the events to the data. And over time, there have been a lot of different ways to process these. Back in the 90s, there was this thing called real-time object-oriented modeling, had an actor model in which it brought events into the data and took care of concurrency that way. Over the years, how many of you basically have callbacks and you try to figure out where your data is and then synchronize against that? If you don't raise your hand, I bet you are lying. It's okay, it's okay. So inside of these small devices, what ends up happening is we have maybe only one core, but we have a lot of hardware engines that are performing tasks. Maybe we have DMAs and timers, and we have different events that are outside of the system that are doing things for us and bringing that in, notifying that they're done, and they need to be serviced. And those are all happening simultaneously. And this is where we end up with our concurrency problem. So Ben's little example here, just trying to do some proxy with very limited instructions, kind of sounds like something we might have gotten from a project manager somewhere. That idea, if you expand that out to hundreds and hundreds and hundreds and hundreds of clients, you start to understand where this problem exists, and it's just a simple proxy problem, right? So how do we solve these problems? One way to solve them, and the way that I'm very fond of at the moment, is with senders. And what I wanted to do right now is kind of adjust our worldview of what senders are. So a sender itself has channels associated with it. It has a value channel, an error channel, and a cancellation channel. How many of you have ever written code where it was really pretty much the happy path, and then later you realized you had errors that you had to deal with? Yeah, okay, good. There are fewer liars in that group, so that's good. All right, then how many of you now, after you got that working and you were pretty excited about it, you realized you actually kind of had to cancel the process or the task because you've been overcome by events, you didn't need the data anymore, whatever reason, and now you had to shoehorn cancellation in? How many of you have had that problem? That's hard to shoe in later. Like error channels, you can usually kind of figure that out, but cancellation ends up being very difficult. Senders have all three channels by design. It's built in, it's what they do. Now, if you had something that took inputs and produced outputs of the same type, that seems like that might be a pretty good pattern for doing composition. And so we can take and just chain these senders together. We can compose them. And as we compose them together, we're attaching channels of the output to the channels of the input. Pretty straightforward, right? So composition is a very, very powerful concept. It allows us to build bigger things out of smaller things, right? We understand that, but we still, for some reason, write structurally weird code, like with statements. So we got to stop doing that. All right, so this produces potential energy. There's nothing there. The sender chain itself is simply the promise to do some work. I can do some work if you want me to do this. I've constructed what the work would look like. This is what can happen, but it's not going to actually do any work yet. You simply described what you want it to do. Now, if you want it to do something, you have to give it to the thing that's going to kick it off and do that work. Now, when you do that, something really magical happens. The state is contained within inside of that unit itself. So normally, state is like somewhere, and your events are all over the place, or you're trying to find state that's scattered about. But state is wrapped. Every time we added another part to the chain, we basically created another wrapper. We keep creating wrappers. Now these are like, don't worry about the overhead of the wrappers. There's no overhead basically to the wrappers. They're like compile time things. But conceptually, we have these wrappers that keep wrapping. And so where's our state? It's in the wrapper. Do I need to worry about the lifetime of the state having problems as the things that are running in the wrapper? No, they're in the wrapper. It's really awesome, right? Now, I hope just in that short little bit, I just hit on a couple of things that maybe you've had problems with in the past. I mean, I know I have. I started programming in '90 professionally in embedded systems. This is a problem that exists everywhere, right? We have these types of problems all over the place. Senders is a design solution to help solve that. There are 3 players inside of this process. The factory will produce a sender. So factories produce senders. Adapters take senders and make a sender. So they're going to adapt the senders that they take in to a new sender type. And then there are consumers. They don't make senders, they just consume senders. And in our example in the previous slide, the factory looking thing is a consumer. Okay, I'm going to be talking about a particular implementation of this. This is the Intel bare metal senders. If you want to know a whole lot more about it, you talk to Ben or watch his talk where he went into great depths in C++ now of how this works. It's open source and it's starting to be used in production. And so this is the library that we use. It has a focus on bare metal, which has some other constraints than others. Like Ian works on stuff that is not in bare metal with senders. And I want you to know, when I follow his chats on the channel, I don't want his problems. He has really hard problems to solve that I don't have. So the bare metal system makes different trade-offs along the way. Sender factories some examples of them are just. Just will just produce a value. Just result of is an example where you give it a set of callables, and the result of those callables are then part of the value channel that moves on. Just error would just produce an error. Result of, as you can imagine, just stopped would be a stopped. There is a schedule function that can be called on a scheduler that produces then a sender that doesn't actually do anything yet, but is where something that's going to be done will happen. There are a bunch of sender adapters inside of the library. I'll just mention a couple here, and then we'll see some of them hopefully in action. Continue on allows you to say that as the stream is moving on, you can think of this chain of events or this chain of senders is moving. I want to continue on a different scheduler. Like, I don't like where I'm running right now. You can imagine this with interrupt context. You don't want to stay on an interrupt context very long. So you get the interrupt context, you figure out what in the world you have to do, what priority needs to be, and you continue on a different scheduled priority. Then you can imagine, do this, then do something else. Repeat, not everybody's favorite. I love it because I like to repeat certain things. We'll see some of that here in a moment. So these adapters, you can think of them as like algorithms that take senders, do something, and then move on. All right, sender consumers, we basically have three. Start detached and start detached unstoppable. So, and then sync wait. People love sync wait, except we don't really love sync wait. So we run forever. We don't stop. Our program never ends. We need to start some things and detach from them. I don't ever need to clean it up, and I don't want to wait on it. I need to get a whole bunch of different things started, and I don't have dynamic memory, and I'm going to do this inside of some static storage, all right? And so I want to start detached. We also have mechanisms to find the detached thing and cancel it if we want. But these are our basic atoms that we're going to build some stuff with. So what does composition look like? Here's an example. S1 would be a scheduler, and I'm going to call schedule on it. Then I'm going to say then, pass it a lambda that's going to return 42. Continue on S2. Take and now continue on scheduler 2 with that result. So it'll continue to pass on the value channel in this sense because I have a value coming through. Then it's going to go ahead and convert it to a string. Now, this comp is not going to do any work yet. It is the composition of the sender chain. I can now say comp, and then if you remember, this was one of our ways to get things going. Sync wait, it's going to block here until the chain completes. So the chain runs, it completes, returns, and then I can pull out of there the value. All right, so here's an example of what composition might look like. We've got a few patterns that I would like to talk about. These are patterns that show up a lot for us, and we've done some things to hopefully make them a little nicer for us. So generally, we have timeout problems. How many of you have timeout issues with asynchronous events? How many of you are not doing asynchronous events? How many of you are doing asynchronous events and have no timeout problems? Thank you very much. The honesty in the back corner. No. So like, timeout is hard. you want to get something going and you got to figure out how to time out. And when the timeout occurs, how do you get it to the place where the timeout belongs? If you've got a callback system, do you call back into the callback to tell it that the timeout happened? And the callback, is it any way associated with the thing that initiated the action that might want to know the callback or that the timeout occurred? This is the concurrency problem, right? Like as we start scattering our state across the system and in our events, it's difficult to reason about. So we want to request a thing. We want to wait n number of units for the thing to occur. If it don't get a thing, we're going to just say we didn't get it. We're going to time out. So maybe it looks like this in code. We've got this thing, and we can use a when any. So what does when any do? When any says, when any of these things complete, then the when any completes. All right, we're going to get thing. And we have this thing called a timeout. What is a timeout? A timeout is just start on the time scheduler for 5 milliseconds. And if that finishes, then do a just error. And so we'll generate an error. And so if get thing completes first, then the other chain will just get canceled. And if the timeout completes first, then the get thing will get canceled. All right. So we can compose this together. We got a thing, and then do something with the value channel, or do something with the upon error, if we got an error instead. Jody.
When a cancel happens, is there anything that allows you to know where in a stream of events the cancel actually occurred?
The question is, when a cancel happens, do you know where in the stream of events the cancel occurred? You could, if you arranged your senders in such a way that you picked it up right after the cancel. So you can get that as an event. Okay, now, how many thought that was a lot of boilerplate for something that we're going to have to do a lot? Nobody? I mean, I did. Oh, thank you. All right, that was awful. How about this, okay? So instead, we have some helpful adapter here for us. Thing, timeout after 5 milliseconds, produce this error, or produce this object on the error channel. Then do a thing, upon error, do something else. So now through this composition, it's very clear what I want to do. I can just read it out. It spells nicely, and I don't have all that boilerplate before. What's under the hood? Under the hood is just the same thing. You know why? Because senders are so cool. You just compose them to make whatever you want. If you wanted to make your own timeout after, you just take the stuff that was in the boilerplate and you simply call it timeout after. And now you've composed a new building block, and you have a building block you can use. Building blocks are really easy to make in senders, and then you can just reutilize the same building blocks over and over and over again. We've got a variety of different patterns that I would love to talk about. Stop, attach. We've got this fixed priority scheduler. Okay, so fixed priorities come in all kinds of different flavors. So you can imagine you have interrupts occurring in your system. Hardware interrupts coming in. You need to do something with them. It ends up that's basically a scheduler. And the priorities are the priorities of the interrupts to be handled. You can just take a fixed priority scheduler and use that for that purpose. Or maybe what you've done is you've created instead software-driven interrupts because you want a task manager, your very own task manager. You could utilize something like that. You can, a time scheduler, it ends up that, how many of you have like multiple time domains inside of your system where it's important to know what time domain you're on? You might have different clocks and such. So we've got a couple folks. So our time scheduler allows different domains of timing to exist. And then this idea of a trigger scheduler. So trigger scheduler ends up being the answer for a bunch of weird hackery that we constantly need to do. Now, schedulers, think about a scheduler for a moment. What does a scheduler do? Well, you give it some work, and when whatever would trigger that scheduler off would go and do the work, then the work gets performed. Now, if you're on a normal operating system, the scheduler is like the operating system has gotten around to your turn to do execution, and you get to execute. Or you think of it as I put some things onto a queue, and when that queue gets executed for whatever reason, then I go ahead and take things off the queue and do something with it, right? Schedulers are places where we get to wait for asynchronous activities to happen. If we think about them that way, then what is a trigger scheduler? A trigger scheduler is a mechanism that allows me to say, I want to schedule some work when a trigger occurs. Now, what is that trigger? Well, the trigger can be all kinds of different things. It could be a message that came in. It could be all kinds of different events inside of the system. Basically, hang out, do nothing, and when that trigger occurs, continue to work again. Now, there are different models and ways of thinking about problems. What do you think would happen if I sat there and just spun, waiting for something to occur, for that interrupt to come in, or that message, or that some event to happen? What happens if I do that? Something might melt. Would you get very good battery life as you're watching your videos? No. Which you wouldn't mind maybe if you're on Teams meetings all day. But once you move over into movie mode in the evening, you care a lot about battery life, right? So you want your systems to go to sleep when they're not doing anything. We don't want to spin cycles. In fact, we want to make sure that most of the time we're actually sleeping as we're waiting for all these events in the system to occur. And when an event occurs, we want to then trigger something to happen and continue on. I don't want to actually wait for a message to come in off of some fabric. When the message occurs and comes in, the hardware will interrupt me. I will get an interrupt. There's something in the buffer. Wake up, go figure out what it is. Hey, it's important. Trigger it now. And the thing that's been waiting for it from the sender chain will go ahead and continue on. Now, these are just building blocks. Robot Tube Man. Oh, I'm so excited. All right, so this is Robot Tube Man. All right, my son-in-law named it. He said, it's like one of those Tube Man things, that just waves in the wind. And I'm like, okay, that's pretty cool. Robot Tube Man. So it's just a whole bunch of servos that are attached, and these servos communicate their daisy chain one to another. It was really great for this project because I wanted to be able to talk to a whole bunch of different things on a chain and create some collisions and make things hard, right? So this is where we are. So you can imagine, well, you don't even have to imagine. They're at the top there. We've got the basic protocol. It has this 5555 start. It has an ID, which will be the ID of which servo it is. It has a length in bytes that will occur for the rest of the message. The command that will be coming, some number of parameters depending upon the command, and then a checksum. That's what the protocol looks like for talking to these servos. Now, if you have seen any of our other talks in the last few years, you'll know that we're very excited about messaging and how to do that. We have an entire message library that deals with messaging. And so we just describe out these fields, the message types, compose them together, and we've got a whole bunch of messages so we can talk to things. So what does this look like if I want to go ahead and ask the temperature from one of these servos? So maybe my temp cycle looks like this. Request the temperature. Then I don't want to stay on the interrupt anymore. I want to get onto a different context to deal with some things. Continue on the display scheduler. Then take what I got in for the temperature and display it. And then delay for 1 second. Repeat. And then start detached. And what is the repeat going to do? It's just going to take whatever the sender wrapper is that it got, and it's going to run that again. So I've created now a mechanism and started it off. For every second, it will go ahead and just pull for the temperature and then get that result and display it. What does request temperature look like? Well, this is using, sometimes we just call it the CIB library. It's an open source library that we have that we've talked about. It has this is where the messaging stuff is. And so I can do message send. And here I'm saying this 8-bit, wow, that's really sad. And now it's going to say other words. There we go. All right. I'm going to take in the ID of the servo, and I'm going to pass that in here. So you can imagine that this is something fancier. Maybe it came in from a different direction. And then I'm going to say send, and here's my servo temp request. This is the message that I'm going to send, and I'm going to set the ID equal to whatever the ID is that it came in. So that's the field for the ID of this message. And then I've got this then receive. Then receive the receive temp, and what message type I want to receive. And then what do I want to do with it? Well, I'm going to get the message into that lambda, and then I'm going to extract the temp out of the message that came in. So I'm going to extract the value out of that field, return it, and now that's how I got the value down there below that I was sending you to display. Now you can imagine that then receive is simply built up using some of the components that we saw already with the trigger. Right? It's just a trigger scheduler. It's waiting for a particular thing to happen, and then it goes and triggers itself and moves on. Why this weird then receive and you pass it a callable, and send, you pass it a callable? Well, it ends up, if you are going to send a message and then get a response, what might happen between sending the message and getting the response? Like all kinds of stuff. Like maybe you even got the message before you registered to get the message and set up for it, right? And so this pattern saves us from that problem. The senders are put together in a chain under the hood so that it sets up the receive part of getting the message before it sends the send, and now it ensures that it's set up for that message coming in. All right. Now, this is the part where the entire talk went off the rails. You know why? Because of Ben. It is always because of Ben. So 2.5 weeks ago, Ben did a thing and it completely deflated my talk. Just like the tube man. So sad. What's going on? All right, I gave a talk on senders at C++ Now this year. And YouTube comments are a mixed bag. Mostly you don't want to read them. User FJ9, this is how you know it's going to be a good one, by the way, says, how is someone supposed to debug code written in terms of senders and receivers? You know what, actually, this is a really good question. It's actually a great question. It's a question that I get all the time just in the embedded world and doing C++ in the style that we do it, which is very modern, very composable, very functional programming, not procedural programming looking. People all the time, how in the world do we debug this? Good question. Now, I don't know what tone this was written in, but that's okay. That's okay. First, you should listen to Jessica and Ian's talk that they gave earlier this week, where it talks about debugging and what you do about debugging with concurrency, and how patterns such as senders and coroutines provide information, higher level information, that maybe can be used and extracted. Great, great talk. So watch that, okay? Now, I had a hunch when we started down the sender path, just like this gut feel, this intuition, that as we enabled senders in our system, we are going to end up with some really cool capabilities. And so I want to walk you down this because this is why I'm off the rails. I'm off the rails because 2.5 weeks ago, Ben posted something new inside of the library with this entry about debugging. And I'm like, debugging? Debugging's cool. Now, debugging might mean something different for all of us, and it definitely meant something different for me than what Jessica and Ian worked on. So I immediately posted, hey, I'm going to work real hard and see if I could do the thing. And Odin, of course, said heart, because Odin lives in this environment, and he would also like to understand what his system's doing. Not only that, there are slews and slews of people at Intel who would really like to know what the system's doing. So when your job is to bring the chip up, like to power it up from scratch, and you get brand new silicon in, just came in, and now you're going to turn it on, but you don't know if the silicon works. Like you don't know nothing. You have zero confidence in anything at all. All you know is that something didn't work. And if your job is like the power management thing that's supposed to be bringing everything up, it'd be really nice to know, why are we stuck right now? So I have all kinds of people who'd be really interested in this solution, wanting to know this. So this is what Ben did. Something so simple. Because I didn't write it. He didn't laugh, so I didn't do it. Ben did it. So what we're going to do is we're going to set up this template variable called handled. It's going to take 3 of these compile time strings. The compile time strings are the name of the chain, the name of the link, the signal that's occurring, and then some magical thing called context. All right? And we're going to write a debug handler, and our debug handler is going to be really simple. When the signal method gets called, we're just going to set the variable to true. All right? What could be easier? Sounds pretty good. And then we have this injection model that allows us to inject behaviors, and we're going to inject this debug handler as the injected debug handler for the system. Okay, cool. This is going to be our sender that we're going to use. Our demo sender is not very interesting. It's actually very boring. There's going to be a just, and it's going to just produce 42, the value 42 on the value channel. Now notice we've started adding some names here. You can optionally put in these compile time names, and this is going to be the name of this link. This link is going to be called link start. And then we're going to do something, followed by a sequence. A sequence just allows me to sequence 2 senders together, get a sender back, and then do something with it. And this is going to be, the sequence is going to be the when all, A0, A1, and A2. When all of these senders have completed, then the sender when all completes. What's A0 and A1 are simply justs. They're going to produce 0 and 1. And A2 is a just that's piped into a then. So just followed by a then. All right, boring, right? Very boring. There's another then, and then a repeat. And then we're going to just start detached, and we're going to sit here and spin the bottom. All right, cool, right? Very cool. Now, at this point, I thought, I'm going to get myself motivated and inspired. In the 90s, I lived in the Silicon Valley, and I'd get motivated and inspired by going to this place called Weird Stuff, which is piles and piles of surplus junk. And I'd walk up and down the aisles, not realizing what I didn't have that I needed, not buy it, and this, get inspiration. I do the same thing with toy stores. Maybe you have the thing that does this for you. But the other thing that does it for me is a debugger. In fact, the only purpose I usually use a debugger for is to get inspiration about what in the world's going on with my particular symbols. So let's go ahead and play a little debugger here. So we're going to load it up, and then we're going to say info variables. What do we have for variables? All right, I love it. I already see that look on your face. Harold is going what in the world? And some of you, your eyes are already starting to roll over, right? That's nothing. That's the mangled version. Okay, let's go ahead and demangle that puppy. So let's throw that in there. We'll demangle it a bit. And then, we're only at the top. Let's scroll on down a little bit further, 208 lines later. But do you see something in here? Yeah, look harder. I see things in here. It's got the word sender, repeat sender, then sender, sequence sender. Maybe if we take and convert the compile time string junk into actually real strings with another Python script, bam, it all fits on one screen, 34 lines. I don't know about you, but I think that context thing, which is, there's the my chain, the last, then, the set value. We're starting to see something. That context looks like it might have something in it. So let's go ahead and look and see if we can find the variable that's associated with our start detached. And bam, there it is. It's shorter. That makes me happier. I don't know about you. But let's see if we can figure something out here. I see an op state. Okay, start detached, op state. There's this repeat sender. Oh, repeat's kind of how I started the thing. Maybe if we just take that sender, and maybe if we now do some indentation to help us out a little bit, repeat the last then, a sequence of before the then, and then we have this link start, and then there was the when all with the 3 justs, and that one is a then and a just A2. Well, that's cool because you know what? sender chains are nothing more than onion wrappers, where the first one that comes in is in the center, and we just keep adding more and more data types, and we keep wrapping it in a larger data type and a larger data type. So we shouldn't be surprised that the symbol information has all the information about actually the sender that I created in the code. It's sitting there inside the symbol for me. Cool. All right, so I worked with Jeff Troll for probably 10-ish years. Very, very, very talented engineer. Jeff worked with me at Ciere when we needed something having to do with like optimize the bejeebies out of this thing, or it'd be really nice if there was a tool that could do this. He was the person for both of those. And I send this video out a lot, and I had just sent this video out like the week before, and so it was on my mind. Like, oh, we can actually do some things with GDB that's pretty cool. GDB has the ability to compile Python into it. And if I took GraphViz, I wonder if I could maybe take that symbol and figure out how to just graph the silly thing. And since I'm already in GDB, and the GDB API is one in which I could actually plug in and get tons of information out of, I bet I could just get the values of what those symbols are and like graph it with it. So, you know, a little bit of Lark, transformers, and Python later, and bam, it's a demo. So let's do one. How many of you love demos? You like demos like you like NASCAR racing because you're hoping they'll crash. All right, here we go. So GDB, demo 1. This is our little demo that we saw earlier. Let's just go ahead and stick a breakpoint at main and get this thing running. And I know watching me type is going to be super interesting. There's probably a better way to do this. Jeff didn't teach me this part. All right, let's go ahead then and say, we're gonna run, so that py just drops you into a Python interpreter with inside GDB. I'm gonna say h equals my async debug. This is gonna do nothing more than search through where the current frame is, all the frames up, find all the symbols inside the system and see, can I find all the handled variables? And form a tree of what they look like and where they are. All right, I found 17 symbols and one chain out of all of those. And let's go ahead and see if we can graph it. Oh, yeah, graphed it over here. Well, I can see it. You'll have to just believe me. All right, here we go. So here's our, yeah, thank you. So here's our sender chain. And my chain is the name of where we started to attach. The repeat is the next part. We had a sequence. A sequence has two halves. It has an A and a B side. The A side had the just link start. That was the beginning of the things. Then we went to the then before the WA then. And then it moved over to the next, the B part of the sequence, which was a when all inside of it. Like this matches exactly what we had. And it all just came out of the symbols. So that's pretty cool, right? I mean, I think it's pretty cool. You can pretend if you want to think it was cool. It wouldn't hurt my feelings. Let's put another breakpoint in 19. This is where we're setting the variable. And let's just go ahead and run it a few times. And then let's go ahead and graph it again. And we just need to graph it. We already have the tree made. Okay, it turns green when it found that the start version had been set. Blue means that we had a set value. White means that nothing, no state yet. And so as we run through, we can see where we are. So how many of you are in like an embedded world? How many of you are in an embedded world where you get to use a debugger? Fewer, but still a few. I don't get to use a debugger. Okay, we ran it a bunch more times, and we're at our last then. That seems important. Let's run it a couple more. Okay, and Oh, bummer. We hit the last then, we started over in the repeat, but everything's still set, right? Because we never cleared out any variables, we only set variables. All right. I don't know about you, but it ends up that if I could dump the state of my system at any particular time, the memory of it, I have already a map file that tells me all the symbols and where they live in memory. And I could take that map file and my dump and produce the exact same information. In fact, if I'm a little more creative about what my handled variable is instead of a Boolean, maybe I can do a lot of other things along the way. So this now has opened up a lot of interesting things. So it's not very interesting, though, if I keep repeating something and I don't clear out my variables. I don't know, maybe it's interesting, but it's not very, very interesting. So repeat doesn't clear. How are we going to solve this? So this is the other thing about working with Ben. He is an inspiration. He has inspirational phrases left and right, including this one, which we hear quite often. It is a simple matter of programming, which he is not wrong. So let's see how maybe we could do this in some way in which I don't want to keep changing my debug code, right? The debug code should just be a library, should just work. And so I want to talk a little bit about some of these tools just so that we have an idea of, if you wanted to do this, how you might go about it. How many of you like template metaprogramming? Oh, that is the right group. All right, so template metaprogramming, pretty cool. The key, I think, one of the keys to understanding template metaprogramming when you're beginning is just understanding that templates are not just code generation. Templates are basically pattern matchers. And as soon as you realize that templates are pattern matchers, it opens up the world that you can just start solving all kinds of problems. So how would we solve this? This is just a type, isn't it? This is a type that has a type in it, that has a bunch more types in it, that has some more types in it. And if I have a bunch of types and I have a pattern matcher, I should be able to figure this out at compile time. So let's get rid of our old debug handler. We get a new debug handler, and cool. It looks the same that we're going to set true, but instead of using the context we had before, let's go ahead and extract a context out of that garbly mess that we have. And the reason we want to extract that context is we want one that's consistent, whether I have the repeat that came in, so I can walk the chain and reproduce a context that's meaningful for everything, or if I got the original sender chain in, that's going to map. I need to pull something out that's the same always. And then for right now, just const expert on start, and if it's inside of the reset recursively group of things, go ahead and call recursively reset. And what's recursively reset going to do? Okay, recursively reset the handled is going to reset the handled for the chain that it has and the context. From this method is just going to basically know what the link types are and set false the right handled values. Okay, there's nothing really interesting in there. It's as boring as you can imagine. Subsenders. So given the graph that came in, can we figure out what are all the subs there? Now we have the subnodes, and we will just call recursively reset handled on all of those subnodes. All right? So at compile time, we're taking the types, we're walking through the types at compile time, and creating these reset handled calls for those types. Cool. All right, so what does subsenders look like? So here's the key to life. Use things that can be composed, like lists. If you have a type list, you want type list of type lists. Why? Because you always get a list. You can take the list and have list of lists, and you can flatten the list again, right? And have a list. So those functional programming people have words for stuff like that, but we won't use them here. All right, so subsenders is nothing more than this flattened list. The default version of subsenders is just going to be an empty list, all right? And what does the one that looks like that's going to grab then? Well, it just matches the stuff that then looks like, and there's the sender part for it, so it takes and creates a list with the sender. What does the version that sequence looks like? Well, sequence has an asender, and it has this other wrapper funky thing, this wrapper, and we need the sender out of there. Here's the wrapper part. Here's its name. Here's that when all thingy. So we just use pattern matching. There's not a lot of code here, right? We just look at what's the pattern of the type that I need to match, pull out the parts that I want, put them inside of a type list, return the type list. Just keep doing that. It's very boring. So when all, I just have a whole bunch of senders. They happen to be wrapped, but that's okay. Pattern matching. I just matched the type on the outer part and pulled the thing out in the inner part that I want. Okay. Demo with a reset. We could do a demo with a reset. You probably just believe it works, and we can just move on to the next one so we don't run out of time. Let's do that. So this just resets. Okay? Okay. So now when we hit the retry, we reset them all back to white, we go back. Okay, now let's look at the other demo. So, you know, this one's really new because it's still in Emacs. It's not even on a slide yet. All right, so what we're going to do here is we're going to use that trigger scheduler. So coming down here, we're going to go ahead and start on a thread scheduler. So we're on Linux, we might as well use a thread. And then we're just going to produce the value 42. And then here is a then that's going to return the value that it got plus 3. And then a sequence of get trigger. Here's the when, or a then. It's going to say got the value if it's on the value channel. And if it's on an error, it's going to say we got an error. And what the value is. And then it's going to repeat. The get trigger, what is get trigger? Well, get trigger is this trigger happy schedule. So we're going to schedule on the trigger happy. And we're going to go ahead and time out after 3 seconds. And we saw this earlier, right? So if I don't get the trigger within 3 seconds, I time out, I produce that error on the error channel, and it moves on down. What is trigger happy? Trigger happy is nothing more than my trigger scheduler with happy as its name, and it's going to have an int. So what's interesting about these schedulers are they can produce values, and how they do that is, don't do this at home, boys and girls, okay? No, we're not using CN, not for real. All right. We simply call run triggers, give it the name, the one that matched above, and a value, and now it will be moved into where our sender chain is. All right? So if I run this, cool things should happen, right? All right, demo 6. All right, it's been 3 seconds, so I'm getting my error. Got another error. Got another error. Let's put in a value. How about 67? Oh, it got 67. All right. All right, that makes sense, right? So we can see how those chains got put together. We could see that the value went through, the error side went through. Let's see if we can run this in GDB. Let's see what kind of a mess this will create. If somebody knows a better way to do this, you need to teach me afterwards, okay? All right. Thanks. All right, we're going through grabbing the symbols. We got one chain, and we probably should have assigned that to something, but we didn't because we're not very smart. Anybody have one of those Macs where the keyboard just like types the wrong letters when you type on it now because it's very old? It's so much fun. Okay, those were my own wrong letters, by the way. That was not the keyboard. Okay, here we go. And now that's the graph for that. Okay, cool. Let's go ahead and let's run it. Oh, no, not that. Goodness gracious, no. Continue would be better. All right. And okay, there's our error. Let's go ahead and do that and see if we can get, padam. Look at that. Now we can see our errors are bubbling through from those calls. All right, so, nobody claps when the cars don't crash. So in this process, which just happened a couple weeks ago, as I was sitting down and talking with Ben, and Ben was helping, we were going back and forth about what this looks like. The end result basically was like context that gets passed in and these debug things should have a protocol to them to make this type of stuff just easy. And so that's going to be coming to the library soon, where there's actually a definition for context that does what you want. You can walk the trees and things of that sort. So, or whatever Ben's imagination tells him that he's going to do. And so if you have ideas, maybe tell Ben.
Does it take advantage of anything in your senders receivers implementation, or is this something that would be able to be applied to the standard that's coming?
Yeah, the question is, can this be applied to the standard, or is it specific to ours? The way that the hooks work is built into ours. Could it work for something else? Write a paper? Is that the proper response? Jessica's smirking, so maybe, yes. All right, let me go ahead and summarize. And you may have seen this slide in presentations of mine in the past. And this is a really important point, I think. We want to talk about the what's, and we want to be in the declarative world. We don't want to be in the hows. We don't want to be in a procedural world. When we can raise the level of abstraction and deal in things that are higher level, it actually unlocks all kinds of things for us. Not do we just have fewer bugs, but things are easier to compose. The whole idea of being in the what is we're dealing with expressions. Expressions compose. Statements do not compose. We want to be in a composable world. We can then build larger things out of smaller things. Perhaps you've seen our Groove library, in which it uses senders, and we have this nice way of talking to registers across the board. If the register ends up being just an MMIO access, right, it's just memory IO access, it all boils down to the exact same thing you would have written by hand. It's simply a memory read or simply a memory write. All the overhead can be boiled away. Abstraction does not have to cost. It costs in compile time. But it doesn't have to cost. And so abstraction unlocks a lot of things for us. In this sense, the sender value proposition is really huge. First of all, I have this problem in which I'm trying to just reason about all kinds of things that are happening in our system. And if I can see it in one chain, this chain is going to perform all the concurrent asynchronous tasks that need to happen. It's right here. I know which scheduler we move to. I know what priority we're on now. I know how we move to the next one. It's just right here. It's easy to reason about and know what's going to happen. It gets rid of a whole set of bugs that we would have otherwise because the state's right there and it's contained inside of that wrapper. I'm not trying to figure out how to grab dispersed state across my system. I deal in expressions and not statements. And that idea of bringing event to state, I can't overemphasize this. Concurrency bugs are often about you trying to synchronize things because you have them scattered about. And if you can actually bring your events to the state itself, you're in a better position. This idea of raising abstractions also enables a bunch of things that it couldn't otherwise. First of all, it enables structured concurrency. And now I'm going to use the word structured wrong, which will trigger lots of people. It also, for me, enabled structured debugging. Actually, for Jessica and Ian, structured debugging. Because we raised the level of abstraction that we were working at, we suddenly now have an understanding of this is the path through the frames across all these different threads of execution that is the logical path that I'm thinking about. How many of you stop the debugger when you have a whole bunch of different threads running and you're like, where does it go from here? Yeah, y'all have done that a lot. And you try to backtrack and then you get to the point where wait, no, Now I'm totally in the wrong spot. What frame do I need to be on now? Oh, this frame, right? Like, because you think at a higher level of abstraction, you can string all that together because you know. Semantically, you told what it was that you're trying to solve. Go see their talk. Structured monitoring is my current name for this. Again, because we raised the level of abstraction, I can actually teach the tools the same semantics that I already understood and told the compiler about. I want to think about high-level concepts. And I really think this is the takeaway. Cinder solves a ton of different things for me. It solves the ability to have a value channel, an error channel, and a cancellation by design. The other thing it solves for me, though, is that higher level of abstraction allows me tooling that I just can't do otherwise because I told the compiler what it was that was my intent. All right. Thank you. If you have any questions, I'm happy to take them in the -14. Whoa, we are over time, but I will take them afterwards. Thank you.